back to normal. All right, let's do this. So I'll show you where you need to look for the course for stuff for today. And we're going to make some changes to the plan for the week. So the plan for the week looks a little bit Spartan right now. Anyway, on the right-hand side, there's a thing that says naming acids. It's a quick check that I want you to do at the end of class today. But here in Unit 5, the current unit, there's the plan for the week of 1-4 to 1-8. That's the current unit, the current week. And it says naming acids and hydrocarbons. And hold on, let's see. Sorry about that. I think I had the wrong screen. Let's try that one more time. Okay, now we're back there. Sorry about that. Okay, so in materials, just go back through it again. Unit 5. Then it's the week of 1-4 and 1-8, naming acids and hydrocarbons. And in this folder, it's actually most of the materials for today. This has a weekly schedule, the plan for the week, and I'll put the Zoom link for the Zoom recording. There's a slide deck here that says, well, it's honors chemistry, naming acids only. And then there's this optional acids naming notes outline. So I'm going to go through material that's in these slides. And this is a notes outline that you could use to help you out. Normally you do it like in class, but this is a good way to help organize your thoughts. There's this naming acids exit slip. That's what I want you to do sometime today, enough time at the end of class. It's a quick check about naming acids and writing formulas for writing formulas for acids. This is a reference for the polyatomic ion chart we've been using. So if I click polyatomics, it just takes you to the polyatomic ion chart, which is a list of polyatomic ions, mostly anions, but it does have that one ammonium cation. There we go. So there's the ammonium cation and the anions, because you're going to need to reference the polyatomic ion chart to be able to help you out with writing names and formulas. This practice naming acids, I'm going to do a few of those with you, but then these are additional practice. You need to practice writing names and formulas for acids. So that's where the stuff is. If you want to follow along with the PowerPoint, you can. If you want to open that up, or otherwise, I'm going to share the let's see, open board. Let's see, share the presentation this way. So let's see, I'm going to go back to the beginning. All right, so you've heard of acids and you know that acids exist. And there's a couple things about like misconceptions about acids. People say or think, or it's like in movies, that like acids are bad or acids are dangerous. An acid is not necessarily bad or dangerous or caustic. It turns out that like the soda that you drink is acidic, acid that's in your stomach, well, it's obviously a stomach acid. There are mild acids, there are strong acids, and the concentration of acids could vary widely. Solutions of water are either acidic or basic. It's possible that they are neutral, meaning that they are neither an acid nor a base. So perfectly pure water has a pH of 7, and that's neutral. You should have learned a little bit about acids and bases in maybe middle school or in biology, but we need to work about like how we name them. So there's a couple terms that are important. First off, acids we say are aqueous. People pronounce that word aqueous or aqueous. Aqueous means that it's a solution in water. So here's the deal. Water itself, like if you have a beaker, and I don't want to do that. If you have a beaker and it has water in it, although water is not really blue, water itself is just H2O. and that water is a liquid. So a thing that you're going to start seeing a lot is that after the symbols for chemicals, we put as another subscript whether the substance is a solid, a liquid, or a gas. And because water is a liquid, like that's like a script like L. Like you can either write solid or liquid or gas. Sometimes you'll see liquid is just like this, except that could be confused with like a 1 or an I. So that's like a cursive lowercase l. You'll see that as a symbol for a liquid. So you have water that's a liquid. And then in that water, you can have stuff dissolved. You could have, sugar. Well, sugar doesn't actually dissolve. You can have salt in the water. You can have gases dissolved in the water, like carbon dioxide. You can have all kinds of stuff that's dissolved in the water. And it turns out that all that it takes to be an acid is an ionic compound which has hydrogen ions, because hydrogen ions present in water makes the water acidic, or in a way, whenever there's excess hydrogen ions, that makes the solution an acid. So acids have to be an aqueous solution. For instance, there's a gas, HCl, and from what you've learned, you would name that gas as hydrogen chloride. And hydrogen chloride is the correct name for this ionic compound with a hydrogen and a chlorine, because on the periodic table, H is H plus and Cl is Cl1 minus. And you put hydrogen and a chlorine, you only need a 1-to-1 ratio, and you get HCl. You would call that hydrogen chloride. And there's a gas called hydrogen chloride. And hydrogen chloride as a gas, I have a little G here, is not an acid on its own. But it turns out that when you put hydrogen chloride into water, and what I mean by put hydrogen chloride into water is you can dissolve gases in water, much like oxygen's dissolved in water. That's how fish and other marine animals can take in oxygen. There's carbon dioxide in water, and that's like the fizz that's in soda. So you can dissolve hydrogen chloride gas in water. And so what happens is when you put hydrogen chloride gas into water, it becomes dissociated. And what that means to be dissociated is that there are hydrogen ions and then separately chloride ions in the water. So kind of swimming around in the water, there are separate hydrogen ions and there are chloride ions. And because there are hydrogen and chloride ions in the water, we name that then as an acid. And whenever things are aqueous, or whenever they're dissolved in water, we write it like this, HCl, and as a little subscript, we put an AQ. So the difference between HCl with an AQ and HCl with a G is that this is hydrogen chloride as a gas. But when HCl is dissolved in water, it becomes an acid, and we give it a different name. And in this case, it happens to be called hydrochloric acid. And we worked with hydrochloric acid earlier on in the class. It's a very, very common acid. Hydrochloric acid is present in your stomach. It's used as a cleaning agent. You can buy bottles of it at Lowe's. It has a trade name other than hydrochloric acid called muriatic acid. People use muriatic acid to lower the pH of water in swimming pools. It's used to etch concrete. So like if you have a concrete surface that's flat and very smooth, but you want it to be rough, you can use muriatic acid. So you can actually go into Lowe's and there's an aisle with paint solvents, and they just straight up sell bottles of muriatic acid, but you got to be really careful because it's incredibly concentrated. So anyway, hydrochloric acid, it has another name as what's called a trade name or a common name, muriatic acid. So the difference between, so what makes something an acid is that it's simply an ionic compound, but it's an ionic compound that's dissolved in water to make an aqueous solution. This word aqueous, like the AQU, refers to like of water or of a liquid. like we don't use aqueous much in our language, but you know, like the Spanish word for water is agua, and the AGUA is similar to AQU, the AG, the AQ. Those kind of letters in the beginning of words refer to liquids or of water. So although AQ and AG are not the same letter combination, of course, when you see that letter combination at the beginning of words, it usually refers to of water. So anyway, that's the basics about what an acid is anyway. So the simple thing to know about acids is they're compounds that begin with hydrogen. So the compounds we wrote before, like I just mentioned, HCl, we would write that as hydrogen chloride. This, H2SO4. So whenever you look at this formula, it must be from hydrogen and then from SO4 2 minus. Whenever that compound is named as a solid, liquid, or gas, it has the name from the hydrogen and the SO4 from the polyatomic ion chart. But whenever you name it as an acid, its name is different. So hold on, let me check I gotta check something real quick here. Sorry about that. Okay, so let me make sure that it's on there like we want it to be. Yeah. Okay, so on the polyatomic ion chart, it says this is just hydrogen because that's like it, and SO4 is on there as sulfate. So you would call it hydrogen sulfate, but if it were hydrogen sulfate as a solid, liquid, or gas, its name would just be hydrogen sulfate. But as an acid, we give it a name that's different. So you're looking for compounds that start with H, and then they're named as acids. So there are two main kinds of acids. They're binary acids and oxoacids. Binary acids are acids that are just hydrogen and a non-metal. Binary, bi means two, and nary means name, or two types. So if an acid is binary, there's only two individual elements. In this case, there's hydrogen and chlorine. So hydrochloric acid is an example of a binary acid. Oxoacids are acids that are hydrogen with a polyatomic ion and have oxygen atoms in the polyatomic ion. When you look on the polyatomic ion chart, a thing that you'll see that's very common among those polyatomic ions, with the exception of the cyanide and the thiocyanate anion, is all of the anions on the polyatomic ion chart, they all have oxygen in them. And there are different naming rules for the binary acids and oxoacids. So that's what I want to show you about how you do now. So first off is binary acids. It's always hydrogen and one other element, and when it's dissolved in water, it becomes an aqueous solution. You name it as an acid. So how the naming scheme works is that for all binary acids, you use the word hydro, the root of the nonmetal, and then ic at the end. So how it works for hydrochloric acid in terms of nomenclature is this. When you have H, which is H plus, and Cl, which is Cl1 minus, hydrogen is just hydrogen. Like that's it. This anion comes from the element name chlorine. So the element name is chlorine. As an ion, you know to call that chloride. So the name of the element has a root, and the root of that name for the element is the chlor, CHLOR. As an element, it ends with "ine." As an ion, it ends with "ide." So when we name these aqueous binary acids, we take hydro, add the nonmetal root, and then make it end with "ic." So because the root is chlor, as the name of an acid, it goes hydro, and then the chlor, and then the ic. So that root of the word with the chlor is stuck in between hydro and ic. You can also know that an acid is binary because it has that hydro-ic kind of name. So chlorine as a gas is just chlorine. Chloride ions, it's chloride, and then the name of the acid has hydrochloric. But you don't call it hydrogen hydrochloric. Instead, acids have the word acid in them. So how it all goes together is when you see HCl, because it begins with hydrogen, we know we have an acid, but the word acid goes at the end. The Cl is hydrochloric, but as the name of the compound, you kind of like swap the names and it becomes hydrochloric acid. The hydro does not mean that it begins with an H. That's not true. The word acid refers to that the compound's name begins with H. The reason that it has the hydro in it is, well, partly because it's chlorine with hydrogen, but more importantly, that is a clue to let you know that it's a binary acid, because not all acids have the word hydro in them, despite the fact that they all begin with hydrogen. So that's the way the nomenclature goes. Here's some other examples of those. So this is in the PowerPoint slides too. HBr, H2S, HI. So what you do is you look at the name of the element, and that's what determines what the name is. Br comes from bromine. And bromine has this BROM, that brome, that's the root of the element name. You know that if you name it as an ion, Br1 minus is called bromide. So we still have that brome in there. It just happens to end with ide instead of ene. But because it's a binary acid, it's called hydrobromic acid. The brome is in the middle of the hydro and the ic. So it's the same here, H2S. This is a binary acid. You know, this is just sulfur as an element. And to know where the root is, you know that we changed the name of that because it's S2 minus to sulfide. So the UR and the ide is what is a suffix. The SULF is the root of the word. Now, there are a lot of exceptions in chemistry in terms of naming. And here's an example. If you were to call this hydrosulfic acid, let's see. Let me look at the IUPAC listing for it. Yeah. So this hydrosulfic acid seems like what you should call it, but this name is kind of awkward here. So it turns out that for sulfur, it stays as hydrosulfuric acid. And that's different than sulfuric acid, which is a different element or a different compound altogether. But this sulfic seems kind of weird to our ear. Hydrosulfic acid doesn't sound right. So hydrosulfuric acid turns out to be the name of H2S. I'll show you how it might be different for iodine. So whenever you have iodine, you know that I is iodide. So it looks like instead of iodine, it's iodide. Looks like how the name looks with that. If you name it hydroiodic acid, that sounds okay, hydroiodic acid. If instead we keep the whole name iodine, it would be hydroiodinic acid, and that's just not right to the ear. So the one exception for binary acids is that with sulfur, and it's also a peculiar element in that instead of it ending with "ene" or "eum," it ends with which is kind of an odd end to the name for the element in the first place. Instead of calling it hydrosulfic acid, it's actually hydrosulfuric acid. But generally, the naming scheme follows just normal. Like brome, you put the brome in bromic, iode in hydroiodic. So I wanted to mix the sulfur in there because that's one exception. So anyway, when you see binary acids, it's just two elements. The name is always hydro, and then the root of the name of the element, ic acid. So hydrobromic acid, hydrosulfuric acid, hydroiodic acid. And again, remember that hydro doesn't mean that it starts with hydrogen, although all acids do begin with hydrogen. Sorry about that. Okay. And we'll do some examples because I want to mix up binary and oxo acids anyway. So oxo acids have names that include names of polyatomic ions. And on the polyatomic ion chart, you'll see that typically polyatomic ions end with "ate" or "ite." In other words, the element or the name of the ion ends with "ate" or "ite." And we have a naming scheme for how you name the acid based upon whether the ion ends with "ate" or "ite." And how it goes is if the ion, that's the name of the ion, ends with "ate," you replace the "ate" with "ic." So "ic" goes with the name of the acid. And also, if the name of the ion ends with "ite," you name the acid to end with "us." Sometimes the non-metal root pronunciation changes to make the pronunciation right. And it's kind of like what sounds right to the ear, but through experience and writing a bunch and naming and seeing names of acids, you get a sense as to what's right and what's not. An acid gets added to the end of the name. So in the PowerPoint, these are the examples that are shown. There's H2SO4, HNO2, H3PO4, and I added H3PO3. You can identify these as oxo acids and not as binary acids because, first off, they contain 3 or more individual elements. And it turns out they all contain oxygen. So sometimes these compounds can exist as solids, liquids, or gases, but when they're in solution and they're aqueous, so sometimes you'll see this will be H2SO4 and there'll be AQ. I know as a chemist, when I see H2SO4, I know people are talking about it as an acid, but this AQ, meaning that the compound is in water, is often added as a subscript afterward so that you know that it's aqueous or that it's a solution of water. Okay, so here's how the naming works. You have H2SO4. You look on the polyatomic ion chart and look for the name of what SO4 is. And SO4 is sulfate. So sulfur is another one of these exceptions to the rule. But the name of the ion ends with either "ate" or "ite." And here the ion ends with "ate." If the ion ends with "ate," we replace that with "ic." So instead of sulfate, it looks like it would be sulfic. but that's kind of awkward. The root for sulfur is actually just sulfur. So we don't call this sulfic acid. That's kind of awkward. Instead, it's sulfuric acid. H2SO4 is called sulfuric acid. It's sort of not exactly incorrect to call it sulfic acid, except that's not what it's called, and people don't say that. But if you were to say sulfic acid to a chemist, they might figure out you actually kind of mean sulfuric acid. So the root of sulfur is actually just sulfur. But no matter what, because the end of the 8 anion changes to ic, the name of the acid has ic at the end of it. And the word acid refers to the fact that hydrogen is the cation. So that first one was actually one that has an exception because of the sulfur. But HNO2 is a little bit more straightforward. I hope that's on there. Yep. The NO2 anion is nitrite. And because the name of the anion ends with ite, we change ite to us. So instead of nitrite, it's nitrous acid. Sorry, my tablet's like slow. I don't know why. But the anion name is nitrite. Ite changes to us, so it's nitrous acid. These two look similar, but here's how the names are different. PO4, that's phosphate. And 8 changes to ic. Now, this is another one of these like exceptions. Let me show you what I mean. If you change just 8 to ic, it would be like phosphic acid. And that's kind of an awkward word. So although it seems like 8 would just change to ic, the phosphate comes from the element phosphorus. And it turns out that the phosphorus has that OR, kind of like the UR in sulfur. So we don't call it phosphic acid, we call it phosphoric acid. What's important is that phosphate ends with 8, and whatever the root for the phos was, which came from phosphorus, has to end up with an ic at the end. How that's a little different than the other one is that H3PO3, that's the phosphite anion. So when you look at the ion chart, you'll find H3PO3, that ends with phosphite, and ite changes to us. So this one's even more awkward, because if you were to call it phosphorus acid, it doesn't sound right to the ear. And again, phosphite is related to the element phosphorus. So we don't call it phosphorus acid, it's called phosphorus acid. Because the phosphor comes from phosphorus. And it's kind of unusual that the element name is phosphorus and the name of the acid is also phosphorus, but instead of the anion ended with ite, it's phosphorus acid. If this were to be a binary acid with phosphorus, the name would begin with hydro and it would end with ic. So let's see. Yeah, H3P, that would be, so for instance, as a binary acid, if it were H3P, As a binary acid, that would be hydrophosphoric acid. That's an R here, because binary acids always begin with the hydro and have the ic in them, and the phosphorus has the phosphor in the middle. So those ones actually have some exceptions mixed in. I'll show you some like clear examples, but generally here's the rule with acids. What's always true. If the anion ends with "ide," as if it were a binary acid and a binary ionic compound, the name has hydro-ic, and this is where the root of the element goes. For oxyacids or polyatomic acids, if the name of the anion ends with "ate" or "ite," then you change the name of the acid to end with "ic" and "us." And all these acids have the word acid at the end. So "ide" changes to hydro-ic, "ate" changes to "ic," "ite" changes to "us." Those are the rules to remember and the guide to help you. So you can also write formulas from names. If you want to write the formula from the name, your clues are, does it start with hydro? If the name of the anion, or if the name of the acid starts with hydro, it's not polyatomic. It's not an oxyacid. It's just a binary acid. If the acid doesn't start with hydro, it's got to be a polyatomic ion. And you look at the name of the acid. If the acid ends with "ic," the anion was "ate." If the acid ends with "us," the anion ended with "ite." Whenever you write the formula, it's important that you have the right charge so that you know how many hydrogens go with the anion to be able to get the formula written correctly. So part of the whole thing with acids and the nomenclature is you use these language cues to tell you whether it's binary or polyatomic. And if it's polyatomic, it's usually just these oxyacids. They're pretty easy to do. So for instance, we do these. Okay, so carbonic acid. It doesn't start with hydro, but it ends with "ic." So that "ic" is a clue about what the anion must have been. So let me go back to this. If it ends with "ic," that means that the anion must have ended with "ate." So this "ic" came from "ate." What you want to do is try to figure out, well, what kind of anion ends with "ate" and starts with carbon? And it turns out there's an anion called carbonate. On the anion chart, you'll find carbonate is CO3 2-. So the reason why there's an acid named carbonic acid is that the name of the acid ends with "ic." It must have come from an anion ending with "ate." This carbon, when you change the name of it from carbonic or carbonic, we don't say carbonic, we say carbonic. From carbonic changes to carbonate. The emphasis in the syllables changes, but carbonate is CO3. So carbonic acid must have come from the carbonate anion. And all acids are always hydrogen along with some kind of anion. So the name of the formula had to have hydrogen along with carbonate. And when you put the hydrogen and the carbonate together, you get H2CO3. So as an acid, H2CO3 is called carbonic acid. If it were to be a solid, liquid, or a gas, it would just be called hydrogen carbonate. But you might know that whenever we named ionic compounds, I stayed away from examples with hydrogen because many of these compounds only exist as solutions in water anyway. So that's the formula for carbonic acid. It turns out that's actually what makes soda acidic because, well, here's how the reaction goes. whenever you put carbon dioxide into water, this is actually pretty simple to see. Carbon dioxide gas in water, this is the chemical formula, CO2 and H2O. You'll see there's two hydrogens, there's one carbon, and there's two oxygens here and one oxygen there. When you put carbon dioxide in water, it makes carbonic acid, H2CO3. Write that with an AQ. So carbon dioxide dissolved in water makes carbonic acid. Just regular soda water, or anytime carbon dioxide's in water, that makes carbonic acid. But carbon dioxide also dissolves in water in the ocean and increases the acidity of the ocean. Okay, hydrochloric acid. Well, we already did this one, but just so you see how it goes, you got the hydro and ic, which means that it must be binary. And if it's binary, this must have come from the chloride, because ide always changes to hydroic, and chloride is Cl1 minus. The other clue that it's binary is all binary acids start with hydro. So it's just got to be hydrogen, and the chloride anion, which is 1 minus, so it's just HCl. Oops, I don't know why I just wrote H2O. And HCl was an example at the beginning. Okay, sulfurous acid. The clue here is that it ends with us. And if it ends with us, it must have come from ite. So us came from ite. And what you'll find is there's a sulfite anion on the anion chart. And sulfite is SO3 2 minus. So if you're going to make a compound with hydrogen and the sulfate anion, it's H plus and SO3 2 minus. And you can do the crossover method or the balanced charge method. H2SO3 must be the formula for sulfurous acid. So how sulfurous acid is H2SO3 is that SO3 is sulfite and ite changes to us. So sulfurous acid, its formula is H2SO3. In the PowerPoint, there's also a flow chart to help you about seeing how the names and the formulas match up together. Generally, if the anion contains oxygen, then it's a polyatomic ion and it's an oxyacid. If the end of the anion ends with ite, then the name of the acid has the root of the element with us and acid. If the anion ends with ate, then the name of the acid ends with ic, so it's the root of the element with ic and an acid. If there's no oxygen present, then it's just a binary acid with a single or monatomic cation, monatomic anion, and the name was always hydro with the root of the anion's element name and then ic. There's that sulfur and phosphorus kind of exception in there that's a little bit awkward. All right, so in the folder there's that naming practice, naming and writing formula practice, and I'll just do like, you know, maybe 2 of each of these real quick. I know we're running out of time. There's that quick check that you got to do. You got to do that this period or do it sometime today. So HF, that's a binary acid. And how you do that is you just look at F. So F is the element fluorine, but you know that as an ion, it's fluoride. No matter what, that fluor is the root. And for binary acids, it's hydro, and then the root of the element, and then you put acid at the end. So HF, F is the element fluorine. As an ion, it's fluoride. Whether it's the name of the element or the name of the ion, fluor is the root, and fluor goes in between hydro and ic. So HF is hydrofluoric acid. Hydrofluoric acid is a very, very strong acid. It's used to etch glass. So when you see frosted glass, you can frost glass with hydrofluoric acid. HNO3, this is an oxyacid. So the NO3, you'll find that on the polyatomic ion chart, and that's nitrate. And because it's 8, that changes to ic. And the root is nitr, niter, from nitrogen. It's nitric acid. Nitric acid is a very common acid as well. So nitric acid, the ic was because the anion was nitrate. There's some other ones here for you to practice, and we're going to go over these tomorrow. So practice these. And then, well, here's some other names and formulas. So we actually just did hydrofluoric acid, but hydrofluoric acid tells you that it must be binary, and this fluor comes from fluorine. All acids, it's H+, and then fluor comes from fluorine, and that's F1 minus. And we'll just do sulfuric acid. Ic must have come from 8, so you're looking for sulfate, and sulfate is SO4, 2 minus. So you got to have hydrogen, and then the sulfate, and that becomes H2SO4. All right, well, we're just about out of time. Try the other examples here and here. They are in, those examples are in the folder as a, I'll show you where. So in the plan for the week, it says practice naming acids. This is the document where I was just showing the examples from. So when you click on practice naming acids, there are some formulas at the top where you can try to figure out the name. And then there are names of acids toward the bottom, and you can write the formula for those. So these are practice, and these are practice. But what you need to do today, as a quick check, there's only 3 questions. This naming acids exit slip. You can do it right now. You got like a minute or so before your next class or whatever. Or you can just do it anytime today. But I got to run to the next class. I'll take questions tomorrow, and we'll go over those, and I'll take any questions you got about naming acids. So that's it. Hopefully you had a great break. It's good to see all your little black screens. I guess you're there. We'll have more fun with acids and bases and naming hydrocarbons and stuff tomorrow. If you have questions, you can put them in the chat. You can turn on your mic, but otherwise I'll see you tomorrow.